Hey there folks, good afternoon. In this video, we're going to work through a harder problem dealing with a ball that's being rolled between two rails separated by a distance of d. The first half of part A wants us to start with a sketch, and then we'll use that to build the center of mass velocity equation. Once we can match what's listed on the screen, we'll move on to the second half, where we take a limit of that expression using these two provided values. Before we start our sketch, there's something important that we need to be aware of. Unfortunately, rolling this ball along these rails is not the same as rolling it on a flat surface. So we'll need the more generalized form of this equation. This states that the center of mass velocity is the product of DIAR and omega, where this DIAR variable represents the distance between the center of mass of our object and the instantaneous axis of rotation. In case you're wondering what this axis represents, here I've taken our ball and I've labeled 4 different points along the circumference. When the ball experiences purely translational motion, all of these points will have the exact same speed, as indicated by these blue vectors. For rotational motion, things are a little bit different, and the speeds of these points are now shown in red. For an object that experiences both types of motion, we need to take the vector sum of the red vectors and the blue vectors, which results in the purple. Notice that the bottom point of the ball has an instantaneous velocity of 0. This is where that axis is coming from. If we imagine our ball rolling along the surface and we draw a bunch of points where the translational and the rotational speeds cancel each other out, we end up getting a line. That line is a segment of the instantaneous axis of rotation. For the overwhelming majority of introductory physics problems, this axis will be located right at the radius of our object, which means DIAR and R are the same. This is why the center of mass velocity is normally expressed as R omega. But in our problem, we have a very different situation. That instantaneous axis of rotation has been pushed upward because of those rails. So DIAR will be smaller than the radius. Here's how we can figure out its length. Let's draw a line connecting the center of mass with the point where the ball touches one of the rails. This distance will be equal to the ball's radius. If you look closely, the lines that we've drawn have created the shape of a right triangle. If we use the Pythagorean theorem, we get the following relation between the sides as seen on the right. Let's take that d over 2 squared term over at the end and expand it. If we subtract that from both sides, and then we take the square root, DIAR is now isolated, and we're ready to create the center of mass velocity equation. If we plug in that square root piece for DIAR, we get exactly what we were looking to match. Let's check out those limits on this equation next. Here we can see that omega doesn't have any dependence on d, so we can factor that out and then plug in our limit value. We end up with 0 divided by 4, and that's just 0. So ultimately, this results in omega r, which is the form of the center of mass velocity for an object that's rolling on a flat surface, like we saw earlier. In the second limit, we're increasing d to 2r, which is the same thing as the diameter of the ball. Like before, let's move omega to the outside. If we plug in the limit value and then square it, we can get rid of these 4's that are hanging out under the radical. What's left is the square root of r squared minus r squared, which means we're really taking the square root of 0. And this causes the overall limit to become 0 as well. So this result is telling us that when the ball is wedged exactly between these two rails, it's essentially stuck and it can't even move. That's all for part A. Part B is another round of expression matching. We're provided with the center of mass velocity of the ball if it were to roll down a ramp from a vertical distance of h starting from rest. It's our job to switch out the ramp for the rails and get the following. Since there's a change of height involved here, it would be a really good idea to take advantage of energy conservation. So let's do that next. We know that the ball starts from rest and that there's no friction involved either. Additionally, we can set the final height of the ball to 0 to make things easy. So these three terms here will all be equal to 0. As we simplify our energy expression here, keep in mind that the ball's movement is both translational and rotational. This means that we'll need to split that final kinetic energy into those two parts. Now that everything is ready, our goal is to isolate that center of mass velocity. But the expression that we want doesn't have m or I or omega in it. What we can do is use our result from part A, and I've included the moment of inertia expression for a sphere as well. When we switch things out for what's listed in that reminder, our equation looks like this. Notice that we get the mass of the ball in each term on both sides. So let's cancel that out. Additionally, let's distribute the square to the numerator and denominator found at the end. We end up getting 1/2 and the center of mass velocity squared in both terms on the right. We'll need to factor those out to move on. The next thing we can do is take the r squared in the first set of inner parentheses on the right and move it over to the nearby numerator. That leftover 2/5 doesn't need its own parentheses, so we can drop those, and then for the remaining inner parentheses, let's divide its numerator and denominator by r squared. Things are starting to take shape a little bit, but we need to get 10gh over on the left somehow. Let's try factoring out 1/5 from the right-hand side. And then we can simplify what's left by moving this 2 coefficient into the attached numerator, and then drop those inner parentheses. There's that 10 that we were looking for. Let's multiply both sides by that value, and then divide both sides by everything in the parentheses. If we take the square root, there it is. In part C, we're going to figure out which speed from part B is smaller and explain why in terms of the energies involved. If we pull up a side-by-side comparison of these two speeds, we can see that the numerators between them are the same. So what really matters is what's in the denominators. In the case of the rails, we know that d is some number between 0 and 2r. We saw from the limits that it can't be 0 because then we would have the exact same situation as the ramp. And it can't be 2r because then the ball wouldn't even move. As for r, that variable has to be strictly positive. We can't have a 0 or negative radius for the ball. That doesn't make any sense physically. Since we're multiplying r squared by 4, and that d can never be equal to 2r, the denominator of 4r squared is always going to be larger than its numerator of d squared. Therefore, this whole fraction will always be some decimal value between 0 and 1. And if we take 1 minus that decimal value, we get another decimal between 0 and 1. And 2 divided by a number smaller than 1 will always give us a value larger than 2. So it all boils down to comparing root 10gh over 7 to root 10gh over more than 7. And since the center of mass velocity for the rails has the larger denominator, it's the smaller speed. That covers the numerical reason behind why it's smaller. But what about the energies? How are those affected? Let's pull up some expressions for both cases. If we start with the potential energy term on the left, there is no dependence on V anywhere. That amount will never change. We have the same starting potential energy no matter what. For the translational kinetic energy, we're taking the square of a larger speed when we use the ramp. So that makes it pretty clear which one is bigger between these two terms. When it comes to the rotational kinetic energy, we end up with the inverse situation. There's more leftover potential energy available for the ball to rotate when it's moving along the rails. We can summarize this by saying the physical reason why the rail's speed is lower is because a larger share of the potential energy is being used for rotation rather than translational movement. Let's move on to part D. Our final task is to find the value of d divided by r when the two speeds differ by a certain percentage. Let's do the 5% case first. When we say that two expressions differ by 5%, this means that we're taking 100% minus 5% of the larger speed. So the smaller speed will be 0.95 times the bigger one. Let's begin by canceling out 10gh in the numerator on both sides. This leaves 1 in its place, and the square root of 1 is just 1. So we don't need the radicals to be stretched over the numerators anymore. Both sides can just be rewritten like this. Speaking of radicals, let's square both sides to get rid of those before we move on. Our next step is to multiply both sides by that giant denominator under the 1. And then after that, we can multiply both sides by 7 and divide both sides by 0.95 squared. I'm going to subtract 5 from the right and then divide both sides by 2. At this point, we can take the inverse of both sides to get this. Let's also take these ratios on the left and right sides and switch their positions. We're getting really close to isolating d squared over r squared, but there's an extra 4 down in the basement. Let's multiply it on both sides to move it over. All that's left is to take the square root and then plug everything into a calculator. We find that a 5% difference between these two speeds arises from a ratio of approximately 1.05. For the 0.5% case, the process is identical. In fact, you can use the exact same final expression and just replace 0.95 squared with 0.995 squared. We just convert 0.5% to a decimal and then subtract that value from 1. Our ratio is approximately 0.369. That's it. We're all done. Here's a quick recap on everything that we went through, minus the steps to match the expressions in parts A and B. If there's any questions, please feel free to let me know in the comments. Thanks for watching, everyone. Take care.